Hello. So I will talk about this reentrancy in Cancun hard fork, the curious case of EIP1153, so transient storage. Chain Security is a smart contract audits firm. We represent many of the main protocols on Ethereum. I'm a blockchain security engineer at Chain Security. I have many years of experience in cybersecurity. I've been auditing Curve, the Vyper compiler, Conic, Yearn, and I've found critical live bugs on multiple protocols. So I will give a quick recap about what Cancun does. I will present an overview over execution context messaging, so how different execution contexts of the same contract talk to each other. I will present how transient storage works, and then I will talk about this new reentrancy vector, which is introduced by transient storage. So the Cancun hard fork was activated on the 13th of March, 2024, exactly 1 month ago. And it contains a bunch of new EIPs that change the protocol. For once, we've got the beacon block route in the EVM. That means we can access the consensus chain from the execution chain. We've got blobs, so this one and this one are for blobs. We've got memory copy opcode. We finally get rid of self-destruct. And finally, we have transient storage opcode. So I will talk quickly about how the data layout was before Cancun. So within an instance of the Ethereum virtual machine, you had the stack, the memory, which you can write to. The code is immutable. You've got the account storage, which has the data storage of the contract, program counter, gas available, not represented here, but also present are call data and return data. These are all the data locations that are present within a smart contract execution. So let's say we have two contracts, C and A, and C calls A, which calls C again. So now we've got a first execution context, C1, and a second execution context, C2, all within the C contract. How can we communicate information from this execution context to this execution context? So it's the same contract, but we cannot use memory, because when you call a contract, even if it's already executing within the call stack, the memory will be new. It will be a new instance. So we cannot write data in memory to communicate between the two execution contexts. That would have been convenient because memory is very cheap to access and to write to. We can use call data, maybe. So C1 can pass a message to A, which passes this message to C2. This can work if A is a trusted contract, so we know what it does and we trust it. But if A is controlled by the user, it can do whatever it wants, and it can lie about the message it received from C1 and back to C2. So call data can work, but not always. And finally, we can use storage. So basically, C1 writes to its own storage, and C2 reads from its own storage, and since they're the same contract, they share it, and they can message this way. This is what happened until Cancun, but it's expensive. So the cost of one S store is between 2,900 gas and 20,000 gas, depending on whether the slot is warm or if it's been written to already. Most of this can actually be refunded if we reset the slot to its original value at the end of the execution. but the refunds are limited by the total amount of gas you are spending in one transaction. So a refund can only be up to 20% of the gas spent. So this is why transient storage has been introduced. EIP1153 introduces these two new opcodes, tload and tstore, and they claim to behave exactly like storage, except that they are reset at the end of a transaction. So now C1 can tstore and C2 can tload, and the value that's been stored in C1 is retrieved in C2. And this happens within one transaction. At the end of the transaction, the value that's been stored is deleted, it's reset back to 0. And tload and tstore cost both 100 gas, so much less than store. One example of how we can use these transient storage opcodes is to implement reentrancy guards. In this case, the execution context messaging would be that C1 says to lock while calling out, and C2 reads the current state, which is locked. So reentrancy guards are implemented like this in using traditional storage. So lock is a storage variable. It's initialized to not entered, which is 1, and the non-reentrant modifier will simply check that lock is not entered, and then it will set it to entered. It will execute the body of a function, and then set it back to not entered. Now, why we use 1 and 2 is a specific of how store costs. So if you write a positive value in a slot that's 0, that costs 20,000 gas. If you write a value in a slot that's non-zero, that costs 5,000 gas because the slot is already initialized. So that's why we use 1 and not 0 for not entered. Anyway, this was the current state of reentrancy blocks, and we've so how much does this cost? We've got one S-load, which is called. It's taken from storage, and it's not been accessed yet. So this is 2,100 gas. Then we've got a called S-store, which costs 2,900 gas. And then we've got, when we reset back the lock, we've got a warm S-store, which is 100 gas. So in total, we've got 5,100 gas spent, but we get 2,800 gas in refund from the resetting of the lock. So if we are using the full refund, it's only 2,300 gas. So this is the minimum cost of our reentrancy lock. Using transient storage, we don't have it in Solidity yet, I think, but we can use it in assembly. And so this is pretty much the same logic. We check that it's non-set, we check that it's 0, we set it to 1, we execute the code, and then we set it back to 0. And now the cost is very easy to calculate. It's just 100 for the first tload, 100 for the second tstore, and 100 for the third tstore. And this ends up being 300 gas, plus the overhead of everything, of course. So this is like 3 cents of a dollar in today's price, pretty much. These would be like 30 cents of a dollar or something like that. So it's quite an improvement. Now we know what transient storage does and how it works. Let's forget about reentrancy guards and talk about reentrancies. I've got a contract here which uses normal storage, not transient storage. It's got a deposit function in which you can increase the balance of the message sender by sending some ether. And then there's a withdraw function, which transfer to the message sender its balance, and then resets its balance to 0. So can you spot the problem? Yeah?
Yeah, you do the transfer, you do the reset the balance after the transfer. So
yeah. But it was a trick question. Actually, there is no problem because, because transfer only transferred 2,300 gas, and this is not enough to recall withdraw again. Calling withdraw will cost 100 for the message call, and then you will not be able to set the balance of the sender to 0 again in the inner call, because even if it costs only 100 because it's a warm storage slot maybe, when you've got less than 2,300 gas in your execution context, you cannot use store. And this is an addition to the EVM that was introduced with the Constantinople hard fork, because initially a storage was always 5,000 gas, and so you could never write to storage in a send or transfer reentrancy. So this was a safe operation. With the Constantinople hard fork, the cost of storage was changed, and it was lowered, and it was, in the least case, it was 900 gas, I think, which was kind of an oversight, because now you could use send and transfer functions to re-enter contracts. So this was detected actually by a colleague of mine back in 2019. The Constantinople hard fork was delayed 1 month because this bug was just detected a few days before the upgrade. So in low gas, when you have got low gas in your context, you cannot have a reentrancy. And this is to preserve the safety of transfer and send with with this Constantinople upgrade. So what changes with EIP1153? Well, the difference is that now EIP1153, so tstore and tload, this tstore doesn't implement this safeguard. If you've got less than 2,300 gas, you can still tstore. So the send and transfer functions are now no longer safe if you use them in a contract that uses transient storage. They're not inherently safe, they can still be safe. So I've got an example here which has a balance field. It's still a vault. It has a balance field and a temporary allowance. Temporary allowance is a transient mapping. We can deposit by sending some ether to this contract, and we can temporarily approve, which means we make an approval which only lasts for this transaction, and this is highlighted as a use case of EIP1153, because usually when you make an approval, you don't want it to last a long time, you just want to do some operations with it. So temporary approvals could be an application of transient storage. And then we've got withdraw all temporary approval from, and this uses the send function, and again, it sets the temporary, it decreases the balance by the temporary allowance. So what can happen here is that I call withdraw all temp from, which sends me my balance. I can do from whatever approval I have. And in this send function, I re-enter temporary approve, set it to 0, and then my balance is decreased by 0, but I've already sent the ether to myself. So now we can use send for this reentrancy. I've got a second example. It's a bit more complicated. but it reflects some code that was in Euler v1, which is actual code in production, which the code of Euler uses storage, it's safe. This one uses transient storage. It's more efficient, therefore, but it allows this reentrancy. So we can defend against reentrancies, but now functions such as send and transfer have to be double-checked if you are using transient storage. What happens here is that we've got a deferred liquidity check option. This is a vault that can do operation. And if we enable the deferred liquidity check, our balance can become negative, which is sometimes useful if we want to chain operations such that at the end of a chain of operations we have a positive balance, but at some point the balance might become negative. This is a way to implement flash loans. So just translating this code from SStore to TStore, we have now the option in this send to re-enter the withdraw function and send ourselves our balance twice. So, in conclusion, transient storage implements data locations which have the lifespan of a single transaction. It's mostly equivalent in behavior to storage operations. They both cost only 100 gas in every case. But differently than storage operations, tstore will work during address transfer even if the gas left is less than 2,300. There's an additional caveat with transient storage, is that if we go back to the example of a reentrancy lock here, we might think, since this is reset to 0 anyway at the end of a transaction, we might want to drop this additional tstore at the end, because anyway, we are locking, we are executing our function, and then since the transaction is ending, this thing will be reset to 0 anyway. So we can save 100 gas with this. This can be tempting, but it breaks composability of contracts. So if you want to execute multiple times a contract sequentially, not during a reentrancy, this will no longer be possible. So it will break multi-calls, it will break batching operations, it will break account extractions such as EIP1153. So this is a caveat of tstore. You should always reset back to the intended value and not let the transaction expiration do it. And operations that we thought would be safe, such as send and transfer, or contracts that we thought to be safe because they only use send and transfer, might not be safe anymore if your contract that uses them uses transient storage. Thank you very much.
Thank you very much, Pietro, for this insightful presentation. We have about 6 minutes left, so let's open the floor for questions.
Hi, yeah, thanks for the presentation. Really interesting. So just to recap, the smart contracts that have been previously not vulnerable to reentrancy, now with the Cancun, are still not vulnerable, right? Unless it's like, unless that contract is taken and redeployed with additional functionality of accessing the transient storage. Am I understanding it correctly?
Yeah, exactly. So contracts that are currently deployed are safe because they don't use the transient storage option, basically. New contracts which use transient storage have to be careful around transfer and send.
Okay, so like if I have a code for the smart contract that has been deployed and in the past I know it's been safe,
Yeah.
if I go and add transient storage functionality, I should account for the reentrancy and go over the code to see if any of the functions are now have been exposed to that vulnerability, right?
Exactly. If you optimize your existing contract by using transient storage, you should reevaluate its security.
Okay, thank you.
Any other questions?
I guess I can ask another one. Yeah. So with Cancun, the transient storage, is there any, I mean, with the next update of, I believe, 64 blobs being added, whatever that's called, the dank sharding, right?
Yeah.
Do you see additional vulnerabilities as far as like transient storage when it's expanded to that many blobs, or is it going to be just?
No, I don't think that touches the transient storage subject, the blobs. And the blobs are really accessible from execution only through the block root, blob hashes, and I mean this is safe. It's not something that's touched. Yeah.
Oh, because in the consensus, is that because in the consensus the EVM execution cannot really access the blobs?
Exactly. Yeah.
That's why it shouldn't be an issue for the smart contract?
Well, you can kind of access it in the smart contract by getting a proof of what's in the blob, but it's not related to transient storage, and it's also, no, it's, okay, so the main reason it's safe, it's read-only. You will not write to it from the execution layer. So the problem here is you can write in transfer or send reentrancy.
Thanks.
Amazing. Okay, one more question, please.
Yes, I remember there was some discussion or some people that wanted to implement the resetting of transient storage at the call level rather than at the transaction level. So when you, what do you think about that?
So at the call level, it would have introduced a concept of a call stack of contracts, which so the transient storage would only pertain to the calls under my execution and not up from me. I thought it was probably a cleaner implementation, but probably it adds a lot to the execution nodes, and I think this is also valid.
All right, thank you very much.
Thanks a lot.